uh, different practical issues that we see in a communication system. So our focus has been on theoretical work, but looking at some of the considerations that we see in the practical world. Then we have done a lot of work on, and yeah, still of a lot of interest is on applying machine learning, adaptive signal processing, and deep learning algorithms for 60 and beyond. Some of the applications are not communication related, but on photonics, we are looking at biospectral analysis for finding out different characteristics of different material from optical means. Also, looking at viability of a seed. We're also doing some work on looking if there's a disease in a plant, how early we can detect what kind of disease there is in collaboration with DAVB, IIT DAVB, based in Indore, along with Soybean Research Center based in Indore as well. Then some of these things you will be familiar. Anyways, it's more comms related. So OFDM, MIMO, NOMA, cognitive radio. So these technologies we are working on. Looking at performance analysis, also looking at some designs, low complexity algorithms for MIMO detection. And some of these we have implemented them in our a practical demonstration as well we have for NOMA and other for spectrum sensing quantity radio. We have been doing this. Then visible light communication, that is the main thing we'll be discussing today for 5G and beyond networks. Then some work because this theme on optical thing. So we are working on optical networks, which is mostly on the backbone networks. So we have elastic optical networks. So currently our allocations are done, the networks are working on WDM, wavelength division multiplexing. Um, but as we move forward, elastic optical networks are becoming more popular. They can be because as we might be familiar with OFDM. So it is similar to say OFDM type. We have a different subcarriers, but their allocation is dynamic. So we are not fixing it a priori. We are giving, let's say, somebody needs a higher load, but this is for a backbone network, right? So here we are looking at rates of 50 Gbps, or 50, because again, the modulation scheme usually is BPSK or QAM. So around the same bands we are looking at. So there we can allocate instead of a fixed allocation, we can give certain, we can divide this band into smaller ones and group them separately. So there's something which we are seeing in comms as well, in wireless comm as well, is coming forward as well, that a bunch of subcarriers are used for one user and the other bunch can be used for other, but they're all form of the same OFDM frame. Then did some work on radar signal processing, basically looking at the algorithms for target detection in case there's a clutter, for small board detection and in presence of clutter. Then we looked at some solutions for industry and defense. So we have, as I said, we have active collaboration in India, with many institutes, along with the one abroad as well in UK, Ireland, Norway, Finland, Czech Republic, recently Canada, South Africa, Saudi Arabia, and the US. Um, we have been externally funded by DST, MIT, SERP, UKRI, Ministry of Education, HRD, or Ministry of Education, AK Finland, TFK Finland, IUSSTF, and others. And currently, we are working on a project on quantum with the US and the UK on wireless and machine learning, and NOMA as well. We are looking at, and then Finland is mostly on terahertz and beamforming, which has recently started. Currently, we have about 138 publications from the group, and of about more than half are IEEE ones, and then we have a few transactions, and then peer-reviewed conference about 165, and around 54 patents have been granted, or 13 filed. The rest are still in the process, and a few book chapters in a thesis. So some of our alumni, they are doing postdocing abroad, or faculties at different institutes, including IITs and IITs and triple IITs. Now, this is the work that we'll be discussing more in detail later. So this is just a small teaser. I'll say we have to know this. So I can probably skip this one for now and then move on. But this gives you an idea of what we are looking at. We're looking at this combination of VLC to TV, VLC to phone, VLC to computers. We are looking at scenarios where even NOMA has been applied. So this work published in 2017, you can have a look, plus others. But at the end of the day, we are considering a more practical system. So not assuming that the system is ideal and giving uh, rates or analysis for network. We're saying that it is ideal, and then things will get X Mbps. But whereas in practice, we'll probably not be able to achieve that because of the system nonlinearities and other issues. So we'll give a more realistic rates that can be achieved, and also how we can improve. Let's say there are some issues in the network, how we can improve it. So now this work we are looking at is on NOMA, where we are considering a heterogeneous network. Will not be covering more detail, but just to give you an idea, if let's say you're working in that area, um, this NOMA is another technique that is coming forward as a multiple access technique. It is not currently made into the 5G standard. There is a study group, but we're hoping in the future there will be. And we're currently executing one project on NOMA with support from IT. Um, so here, basically, I'll just give an overview that in the courses and in our theory, when we were reading, what we are teaching, we say that you have to go orthogonal, either in time domain, frequency domain, or in space, or in the code domain. So somehow you have to try to go orthogonal, or in space you can give some kind of diversity there. Uh, but this NOMA is, philosophically a different way of thinking. We're saying that yes, you can go non-orthogonal, so you can introduce some kind of non-orthogonality um, in time in code. But if you do if you do it cleverly, then you might be able to use the same time and frequency slots, the full slots, for more than one user. So you can have two, three, four users that can be served in the same time and frequency. But so that is, for a mobile operator or a user, it is very interesting, because with the same license, fee that they have paid, they can, in theory, get twice the number of users to be served. So it's a very interesting technology that is going to work with not only with in the 4G or 5G scenario, but it is basically a technology that you can use with. So we're now, let's say, exploiting with IRS. So IRS may come in 6G or 7G, but if you look at full duplex energy harvesting, so this it is one of the base technologies that can be, it is compatible or can be applied with other technologies. So it's not, you know, compared. So millimeter wave we have applied it to as well in MIMO as well. So this is a lot of place it can be applied to. So we did some work on visible light as well, as I said before, and showed some practical insights. How many users you can serve, and what happens if, let's say, you keep on increasing the number of users. Do you still get the gains or not? Then this is some work we do in the backbone optical networks. So here we have um, you see different nodes which are connected through optical network. So I mean, this is very important as well if you're looking at from the end-to-end communication system point of view. That see our these courses, conferences online these days are all happening because we have very good optical network connection. Because they carry the the data in gigs. So they're like trunk lines that we used to have in telephone systems. So they carry a huge amount of data. Now optical fibers are coming to our home as well connections. So they're very reliable medium, and actually they can be used along with visible light as well. That is something of a future work to consider. So here we have these these things, and they are connected with data centers. And our focus has generally been on, if let's say there is an earthquake or some other thing happen, there's a cut in a submarine cable, then what kind of routing strategies can be used for elastic optical network, which is again expected to come in the future. Now, this thing is something that we're working currently is on quantum key distribution. We're looking at secured optical networks. Now, this is the next, I think, thing that we'll hear a lot in this decade on quantum computing, quantum communication, quantum everything. So our focus is with quantum communication, primarily on moving of these quantum keys around this. So I'm seeing actually some work on VLC as well using QKD. So this is also a very interesting area. But our focus has been on the so far research focus has been on the uh, fiber optic communication system. We're looking at how QKD can be transmitted, and also in these scenarios, if there is some earthquake or something happens, if you're less interested in this area, I'll suggest you read our it's a recently published Open Journal of in Open Journal of Communication System or Society by IEEE as a review paper. So that gives you a overall view of what is quantum key, what is quantum key, and then what is happening in this area of optical networks in terms of quantum key throughout the world. What is going on? And this so again, if you're from comms background, you can relate to. Hopefully, this is on cooperative network. So we have performance analysis of multi-hop relay wireless communication systems. We have this optical fiber connection. Then we have it's connected to a certain room, and then let's say there is no connection between the two rooms. We can do it through some frequency translation. So from optical fiber, we can go to millimeter wave. From millimeter wave, we can go to UHF, and UHF we can go to the millimeter wave again. And the lastly, as I told you, we are working on the systems where, let's say you have uh, a system imperfection. So here we are looking at systems where we have um, there's a nonlinearity there from the RF amplifiers. So because of this nonlinearity, if you look at this top right figure, that shows that the power amplifiers that we use, they are not linear devices. They will introduce some kind of a nonlinear behavior, and that will have an impact on our communication systems. There will be interferences uh, that will occur. So in those scenarios, how we can, what kind of rates that we can expect to come from these communication systems. So our focus has been on cooperative network mostly, but it's not limited to cooperative. And also we have looked at various newer forms of modulation techniques. Modulation. Yeah, so we have looked at, let's say, Starcom. We have looked at hexagonal com and looked at its performance in various scenarios. So if you're interested, you can refer to some of our previous work. And if you're less interested towards looking at the nonlinearity aspect, which is now again becoming very very popular. But we have been working since 1916, 2016, 2017 onwards. So we look at this magazine article, which gives you a brief overview. So there's not much mathematics involved. It gives you an overview of the effect of nonlinear power amplifiers on future communication networks. So with that, I'll move on to um, our topic today. Well, change slides now. Oh, sorry, I was muted. So yeah, um, just a query. How many have heard about visible light communication before, or have worked on visible light communication?
This is the question from participants. Have you ever worked on visible light communication?
Yeah, so you can unmute or maybe write in the chat box.
Yes, sir.
Okay,
In the chat box, we got a few responses.
sure, sure, sure. So there's not
Aviranjan
that many.
also.
Okay, so there's probably not that many. Yeah.
Yes, sir. Yes.
Okay, okay, that's fine. So I'll go slow. I'll start from the very basic, and well, probably after this talk, you'll be more, interested in sort of, let us say, maybe take this as a future, area of research or exploration. So this is something I gave in the worldwide forum that was invited talk in 2nd December it happened in Paris this year, so it's running remotely. So there, so I'm basically, yeah, going to do a repeat of this in a way, but I'll give you an idea about what is going on. So as WWRF, which is responsible for bands allocation, so they are also now looking at this. And in this year's WWRF, so as I had this invited talk there was a full session on the day after on visible light, where they were discussing on different areas of visible, because that is something which is coming to the market, and that's what I'll try to cover today. We look at some of the practical implementation. So it is so maybe maybe because you don't see them at the moment, there's not that many people probably working on it. So we'll see that in detail as well today. So what is visible light communication? So visible light communication, as you know, not many people are aware as well. So we'll go. Let's go and start from the very beginning. So visible light communication has emerged as a promising green and interference-free supplement to RF-based systems. Now, why we call it all these terms? Why we call it as a green? Why we call it interference? This will cover them in detail in the next few slides. Um, Now, VLC relies on uh, okay, the VLC relies on intensity modulation of LED according to the input uh, message. Um, it is, you can think of it. Let's say you are, having a light, so you're switching on and off it very quickly, so that so that to a human being, to a human eye, it seems that it is continuous, right? But although it is still, in simplest form, it is, let's say, switching on and off LED is very fast. A very, low rate forms we have seen in case of infrared remotes for our televisions. We have been using for many years for air conditions and all. So these things have been there, but now we are looking at from visible light uh, 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 you know, uh, point of view, from that view, and which is the higher bandwidth and other advantages as well than infrared. Um, Now, visible light as such covers the wavelength from 380 to 750 nanometers. So if you look at this uh, uh, plot, uh, we see that we started with AM, so that is on the on the rightmost most corner. Then we move towards shortwave, then television, FM, radar, infrared. Now we're in the visible. After that, ultraviolet, X-rays, gamma rays, and all. So here there's a huge bandwidth. So this is a very big advantage for us in visible light communication system. So the advantage of VLC or RF is that we have a huge band. So RF, we are limited to the bandwidth, and a lot of these bands are occupied or given for different purposes, and that's why you hear a lot about auctioning of these bands, 2G, 3G, and others. Um, so these are the uh, bands which are you know very expensive, and the service providers like Airtel, Vodafone, Reliance, and others, they would bid for these, and they go for very high prices, in crores for different regions, and that forms a bulk of their the operators expenditure, and they're given for a certain period of time as well. So it's you know yeah, for state, for government it is good because we are selling something which is there, but we're getting revenues from it. Uh, but that is very expensive for the operator, and those ultimately comes to the consumer as well. That is um, because they're all working in a licensed band. Whereas if you look at, let us say, if I look at this the um, Wi-Fi that we have been using in our homes and all, we are transmitting because we're doing RF transmission. We are transmitting without purchasing a license. Uh, so, if you're to, so transmitting in a licensed band is not permitted. We can't do that. Uh, Whereas in case of unlicensed or non-licensed bands, we can do. So that's the advantage that we get when we do a Wi-Fi because we are still transmitting in radio waves. Have it in our offices and other places. So this thing, so the main one of the main reasons for it to become popular for Wi-Fi was working on non-licensed networks. So similarly, uh, we see this is advantage with visible light communication system because in order to, let's say, put a lighting into to put a bulb in your home, you don't take a purchase a license, right? You purchase that light and then uh, just install it. And so it is transmitting optical signal by optical waves, but you don't have to purchase a license for it. And the bandwidth is huge as well. So as compared to RF, so 430 to 770 terahertz, so it's a huge band. Now it is low cost and easy to implement since it utilizes LED infrastructure. So over the last decade or so, we have seen that uh, there is a move from incandescent filament type lighting to LED lighting. We are seeing it in our homes. We're seeing it in common places, airports, railway station, bus stations, banks, everywhere. We're seeing it, and street lighting as well. It's moving towards LED driven lighting. Then we're also looking at these lightings from another, in our scooters, two wheelers. Lighting is also becoming LED. In four wheelers, it is already there for both front and rear lighting as well. So it has become part of our lighting infrastructure uh, globally. So and it is not very expensive. So we can use the same network for data transmission as well. Then it is energy efficient because we are using it. Uh, so if you compare the power required to do RF communication systems, so LED is very low. LED bulb itself is very very low power, and we basically what we need to do is a small electronic device to do modulation and transmit it across. Whereas for RF, we need a full RF chain, so we have a high power amplifier. We need to do IQ conversion, synchronization, and others. So they take a lot of energy. So here it is energy efficient. And hence, it belongs to a category of green communication technology. So it is immune to interference as well from EM waves. So as we see in case of Wi-Fi or cellular network, there's a lot of interference, and a lot of these interference from ignition of the car to uh, in the cities, like if you look at the metro and other things. So they're mostly all in the RF lightning as well. They're all in the RF electromagnetic bands. So they call interference in the EM bands, and uh, we have also seen that, with let's say if you're living in a multi-story block of apartments, or if you're in a busy airport or busy center of a city, you'll see a lot of these Wi-Fi devices being connected. They are all interfering with each other, and because they're all working in the same band, and they interfere with each other. So your rates uh, are lower, and so you have these you have to deal with this high interference. Although they're all working in ISM band, but they're all transmitting, and that band is very limited. So they will interfere with each other. So this is not there for visible light communication system at the moment. There's not too many devices. Although even in future as well, because visible light cannot go beyond opaque boundaries. So there is an inherent security and also immunity from the interference, because in case of RF, because RF in current bands, it can pass through the walls, through doors and all. But this cannot happen for visible light, because the opaque boundaries will confine this visible light within that certain that room. So the high security is already there. Now, one thing could be that you might have windows, things in the room, but again, the light cannot travel very far from those windows, and also even if somebody is trying to do eavesdropping or do a security thing, then you can still possibly see the person from the window as well. So it is um, difficult to do eavesdropping or do a security breach in case of visible light communication system. So it provides a threefold goal of illumination. So lighting, we are doing it anyways through visible light. Our energy bills have come down because of moving towards LED type of lighting. We can do communication, as we'll see now how we do it for visible light, and then energy harvesting as well. So we are seeing some of these deployments using things like solar panel as receivers, even photodiodes. They can harvest the energy and then do the decoding. So it can be a perpetual and a light energy source. We don't need to have these connected towards through some kind of infrastructure to power up these devices. There is a high SNR due to high illumination level, because when we're doing illumination, we require a higher lighting. So in a way, it has already got a high signal to noise ratio. Then we have this different applications in uh, light fidelity, Li-Fi systems. We have smart lighting. We have uh, say for RF environments like hospital, aircraft, and this is actually coming to aircraft as well, some of the new deployments. Then intelligent transport system. So vehicle to vehicle communication can happen through this. Vehicle to infrastructure communication can also occur. Then different IoT-based applications, wearable devices. Also, we are seeing Wi-Fi being installed. In some places, we are seeing that in some cities that the street lighting is LED controlled. It can change the color as well. Okay, not for communication, but LED is there. You can change color based on either for aesthetic, for look reason, or some event is there, some occasion is there, or it also will used for security. If there's some event, so untoward incident is happening, then they can switch on and off the light quickly, so that the the burglar or someone may know that somebody is watching. So it acts like a deterrent as well. So smart lighting, and these are um, you know smart lighting poles. They are all coming into deployments. Now this gives again a very big picture of where visible light communication is coming. We're looking at personal area network where we have conference halls. Um, we look at some real pictures how it is done. So we have different lights on the ceiling, and they are showering this data on the downlink, and we have different devices which are collecting this information. We have different transportation hubs in the bus station, as said, in airports and other places can be used. You can use in home and office environments. Use data showers, like this I was telling you, that there could be different light bulbs which are providing lighting, street lighting, along with the data. So currently we have to install this lighting plus, let's say, a Wi-Fi network to provide Wi-Fi throughout the city. But here we can use the lighting infrastructure itself to provide this data as well. Uh, then transportation system, so vehicle to vehicle communication can happen. So vehicle at the back can transmit information from their front lighting, and the vehicle in the front can use the backlight to receive this information, also transmit some information from backlighting to vehicle to infrastructures. We can use these you know uh, traffic lights to send some information like what is the traffic condition in the front, or some information system like some things about let's say COVID or some other information that can be transmitted. Also different signs like stop signs, all they all can be done again through vehicle to infrastructure communication using visible light. Then this is another very interesting area of applications with sorry non RF friendly environments where we have risk of exposition. So we have that's exploration and all we're doing. So there's let's say different we have mines where say RF is prohibited. We have refineries where RF is prohibited in chemical plants. It can be used in hospitals. It can be used. Also being used in underwater. Security is something I already told, because again this is the light cannot go outside and somebody eavesdropping is difficult. And hospitals, airplanes, and those, it can be used as well. There's smart lighting where indoor positioning. So this is one application will show right, where it can be used for let's see different. You can tell in the supermarkets where it can tell you where different offers are there. You can go to that particular product once you made a sign, so that you can do. Then augmented reality is another thing, because you need very high data rate there. Of course, entertainment as well you can do in shopping centers and other places. Then it is again a replacement for cable for smart smartphone applications. So these all can be driven through a visible light communication network. Now there are major companies working in this area. So some of them are like Pure Li-Fi. So this is a company started by Professor Haas at University of Edinburgh. Now he's moved to Strathclyde University, where they have made this product, Pure Li-Fi. So this is their company where they have made a product uh, of different things. So I'll look at different products that they have come about with. So here we and then there is Firefly Wireless Network. It's a VLC and infrared lighting company with light motive of France. They are also developing different uh, products on visible light communication systems. Then we have Oldecom. It's a French telecommunications company that it's research with again a university in France. They are working on making products on visible light communication systems. And after that, we have uh, VLN Communicoms, which is a US-based company, which is also working in developing products for visible light communication system. Then, interestingly, you will see another list below, which is Signify, Lumen, Cipel, Li-Fi. We have Philips and Wipro Technologies. They are also working on uh, this VLC based systems. Now, uh, what has happened again is we have moved away from incandescent to LED lighting. We are seeing that the companies which are big in lighting, they are moving towards the communication systems, because this serves to them as a additional or a, a new revenue source for them, uh, because this can So what has happened? See, with the incandescent bulbs, they used to go bad very often, right? So we would need to replace them after every few months, or a year or so. But with LED lighting, their life is very long, so there are not many being changed. So for the lighting industry, this becomes an option that they can, sustain their businesses by moving towards this from the Li-Fi, from the communication point of view as well. So that's where we are seeing in India, Wipro is playing a big role, and Philips is also doing is playing a big role in this. We'll see some in detail. Now there's a new Li-Fi products are getting launched almost every day, and then there's a new lot of companies are also coming. It's a green area. It's a fresh area with a lot of scope for new startups and all coming in. Now there are different products. We'll look at some of them. Li-Fi Max, My Li-Fi, Li-Fi. So we'll look at these in details next. So My Li-Fi is like a desk lamp where each user can connect to internet through optical signals emitted by tabletop desk lamp. So you're seeing that there is a fiber optic cable coming, right? And then the lighting is through this fiber optic cable, and that is also giving us data as well. So up to 7 connections can be accommodated with this secure link. It provides transmission speeds of up to 23 Mbps for downlink and uplink. So this is huge rates that you're getting. And Li-Fi Max, this is a fast and secure connection free from again radio waves. So what they have done is this lighting which you can put up, and if you look carefully, there is a small the this a LAN cable that can be put there. So plug and play system that can easily be installed in a room. Guaranteed 100 Mbps download and uploads speeds, compatible with different type of operating systems, and a Li-Fi Max can support about 16 users. Then Wi-Fi Li-Fi lamp. So here it can be used in areas where RF is not allowed in some hospitals in certain regions, just not allowed. So that we can use um, Li-Fi based systems. Then this is a dongle that you can purchase off the shelf. Uh, it's from Pure Li-Fi. So this one is like if you have to connect to a cellular network from your laptop, you would connect this small dongle and connect to this, put a SIM and connect to the cellular network. So similarly, for Li-Fi, you can use this dongle connected to your laptop. Again, it's compatible with Windows, different version, Linux, Mac OS, and all, where you can get up speeds up to 42 Mbps. Those are one of the first dongles that are available from Li-Fi. So if you have, let's say, one of these, put on the ceiling, or even this in your desk, and use one of these dongles, you can do communication using Li-Fi. So you are, virtually RF free environment, because there's a lot of news about RF, being not good for health and other things as well. So that is where light can play a important role. Then we can also go for a secure link for different vehicles. So interconnected, as I told you, that the vehicle behind or vehicle in front, they can communicate with each other using again Li-Fi, or so there's this product called Vehicle Secure Link, and then there is another extension to that product is using them on the traffic lights, so that can also transmit information, get connected with the traffic signal. So these are real products. Then office secure link, again, so office lighting from point to multi-point. It can use actually different colors as well. So red, green, blue, or invisible, infrared as well. So there's various options. So you can actually use it even in case so there's one the query that usually comes, question that comes that, no, it is visible light, but I can use my Wi-Fi even if the light is switched off. So can I use it then. So you can use it there as well. You can use it so the SNR level will be low, but we can work in this dimming region where the the SNR level is quite low, but still we can do communication there. So even if so you are sitting in dark in your room, you can still do visible light communications if there's a provision for dimming to work in the dimming area. Uh, Now it is applicable to both. So this product is applicable to even infrared, so that you cannot see. You can also work with infrared for point-to-point or point-to-multipoint connections. Then it's applicable to any indoor environment like office, conference room, etc. Then there is another product called Luminex. It's Wi-Fi enabled LED panel on the ceiling. So uses Ethernet port available through which LED panels can provide wireless internet access. Wi-Fi systems use hybrid visible light links capable of providing data transmission speeds up to 70 Mbps to 60 Mbps. Can cover an area of this can handle 15 simultaneous users. No Wi-Fi trials in Orkney, Ireland. They have done in Orkney Island. Sorry, in it's a small islands just off the mainland Scotland, where they connected these through optical connections. This was a project handled by there's about like, yeah, 389 rural towns, and their slowest speed was about 6.3. And there was this project started with the University of Edinburgh, Pure Life High, and other councils and municipalities coming together. So there they installed this system to connect this small island through the mainland through optical connection only. Then in parallel, there is a 6G flagship uh, project going on so we are also partnering there. It is with the University of Oulu, based in Finland. So they have made this again different panels that can do visible light communication that can give you a very good download speeds. You can look at a small demonstration here on this YouTube link. If you want, you can copy this link or take a snapshot of this slide and run this through. You can go through this um, video. So this is work by Professor Kaas. They've done a demonstration, tested how radio and light can come together. So they are, because there is an issue that the visible light, okay, it is secure, but then if you move from, let's say, one room to another, or if you're moving from one floor of a building to another, then there might be regions where you do not have the connection through the Wi-Fi system. That's where RF can take over. So it can work seamlessly between RF and visible light. Uh, so the switching can happen. For example, if using VLC and source light is interrupted by some reason, so this is then connected to the radio network and vice versa. So that's what they have demonstrated. Then there's another one by Philips Lighting. It is connecting a laptop or tablet with this dongle from Pure Li-Fi. So this is also, world's first Li-Fi office, where the full lighting is through Philips Lighting, which is visible light operating, and then there's a small dongle that can be, because again, currently our devices um, do not support high, they do not support this because our laptops, they don't have a Li-Fi panel, but maybe in the future they will be making part of it. Um, so this is again there's a small video here. You can visit this website and on the in YouTube, and you see the video. We can take a small, yeah, screenshot of this. So then the Pure Life, they so Philips, actually, this office is office of a big real estate company called like Lecarde in a La Defense area of Paris. They have demonstrated an uninterrupted Wi-Fi connection, presence of natural lighting as well, because there's always a question, what happens if there's ambient light. So they do work. There is certain issues there, but they do work. There some rates will come down, that is okay, but still it will work. And also in the user mobility, so that these things also, we have considered in our research work as well. We'll go to those in later slides. uh, then then we okay, let's move on to this one, the car. Okay, the Hegel gymnasium. So the school called the Hegel Gymnasium in Stuttgart in Germany, where they are put this lighting infrastructure, right? And there are the students who are sitting in this, they will sit on the different benches. They can be, so the Fraunhofer has done this prototyping uh, in, uh, in Stuttgart, where they're using these for, again, for, so instead of a wired thing, they'll use this Li-Fi links for communications. Then in Kyle Academy, it's uh, a school based in Scotland, where again pure Li-Fi and University of Edinburgh, they combined, came together to use Li-Fi XC systems to connect these up to 8 Li-Fi enabled LED bulbs, which are connecting to, this dongle connected to the Li-Fi system for communications. So if you've not seen don't, not seen this before, so the the professor on the first one on the right hand side is Professor Haas. So that's his company. So it's big in the Li-Fi. So that's his company, Pure Li-Fi, and there's like tremendous work in this in Li-Fi region. Then Philips has done this lighting at Carrefour. Carrefour is like our Reliance, big store, DMart, and this big shopping center, where basically for grocery and things, where uh, they have installed this lighting infrastructure, and you can use your handset to do the to do the communication. So this is actually very interesting. Let me see, is it possible to, yeah, maybe there's a possibility. Yeah, so I might just play this as a few minutes short video that you can see it in action. So it's not merely a theoretical concept anymore. It is coming to light. So I'm trying to open this in the browser. If it opens up, uh, then I can play a short video and attach this process then. Yeah, so I can do this. I'll need to stop this one and attach to the browser. Yeah, so you can see this. So you may not be able to hear it because of this microphone and things, but let me just play it. So just a 2 minutes uh, clip.
Philips has just completed the world's first major full-scale installation of 2.5 kilometers of LED light features for Carrefour that contains patented LED-based indoor positioning technology.
So this hypermarket is the first hypermarket in the world where the Philips LED-based indoor positioning system is installed.
We work with Philips on energy savings, and we wanted to test a new service in Carrefour Lille and go beyond just lighting with using a new app for light. The focus we made is to just specify and localize the promotion for people.
Philips LED fixtures that are installed in the store use VLC technology, visible light communication. Each luminaire sends out a unique code that can be directly detected by any smart devices using a camera without any additional device or accessory.
Philips LED lighting acts like an indoor GPS. Each Philips LED light feature transmits a one-way location signal to a shopper's smartphone. To to trigger Open an App that provides location-based services.
The main benefits for customers through this new application is to prepare a shopping list with his promotion, and when he arrives in the store, he can localize all the product he chooses.
For Carrefour, this is the opportunity to offer location-based services that will enhance the shopping experience, making it more interactive and personalized.
But the lighting technology not only provides positioning, but also orientation and an incredible meter accuracy.
So in this store, Philips LED lighting offer energy savings, quality of light, but also act as a real platform for indoor positioning. Philips LED lighting goes beyond illumination only.
Waze, Google Maps, navigation has become a standard, and it works incredibly well outside. But there is no real solution yet for indoor navigation. Your mobile device goes blind walking into a mall and will not take you all the way to the store. Sonorex changed all that. We've developed a unique protocol based on sound waves beyond hearing range that enables navigating inside any building and even underground with amazing precision. It works by using any simple speaker used as a beacon. We deploy a few in a building, such as a hospital, an airport.
Right, so I hope you were able to hear it. I'm trying to get the mic closer to the speaker here. So this is, these are real deployments, and this was a video from 2017. So since then, a lot has happened. More things are going on. So here, it is also used for checking the stock availability and helping in automating this, system for the customer. Also, it helps in localization because with Li-Fi, we can do far better localization, within a shopping center than with Wi-Fi or with GPS. In most places, most indoor places will not work. Uh, so it can direct you to places where you have to pick up your shopping from. Now, this is all the good news. Now, there are certain issues with it, with the Li-Fi, as with the other systems as well. So we have to deal with these issues. So let us look at what are the major issues which impact from the communication or baseband processing people point of view. So here, one of the major ones is LED nonlinearity. So because LED are the semiconductor devices, they are nonlinear. They have a nonlinear behavior. Um, so they result in additive distortion at the receiver. So this needs to be handled um, at the receiver or at the transmitter. There are certain schemes. We'll look at them. Then intersymbol interference. This is something we have known from communication systems. You have a time dispersive channel, and then there's a limited bandwidth. So it does then the symbols will interfere with each other. That needs to be corrected. So this is existing in visible light as well. Then user mobility. So this leads to a multiplicative fading distortion and degrades the real link because user is moving in different areas, leads to outages and non-Gaussian distortions. Then another important one, because we are working in this you know region of DC biasness is required here, because unlike the RF communication system, where if let's say if I consider a QPSK modulation scheme, let's say, um, or even if I say let's say BPSK, it will be very simple. So it is, we can say either plus plus EB um, underscore square root of EB, and then or minus of square root of EB levels. Now plus one is fine, but negative one in case of a physical or optical communication, that is not, because after zero it is switch off. there's nothing there. But okay, for BPSK, you can say on and off. That is one way of signaling. But if I go to QPSK or QAM schemes, then I need two levels there, right? So I need um, on and off is okay. In the plus sign, it is okay. If let's say my x-axis is on the looking at the positive sign, which is the when the it's a positive DC voltage where the LEDs will be switched on. Um, Here, what we do is we can provide what we do is we move these points in the by providing some kind of DC bias. We move all of them towards a region where it's a positive quadrant. So there, then because of that, to move all my constellation points in this positive region, I need to give a DC bias. So that makes this system, visible light system, to be, you see, uh, to be, you know, um, you see, sensitive to this DC bias error, which is not there in the other type of system. So this is something again we need to be um, careful of. So we need to be handling this uh, this too. So we need to be from signal processing point of view or machine learning point of view. We need to be handling these impact, and also many of these are not fixed; they are dynamic things. So, for example, um, one of the simplest solution to uh, do is to use a lookup table kind of solution. We'll look at these solutions in just in the next slides. So let's see that for the visible light, there is a performance gap between the promised one in theory and the practical one because of these system imperfections. The throughput can also be increased using a massive MIMO that is there. And there's something I didn't mention before, that in case of a visible light system, we have multiple of these LEDs. So these LEDs can be used, I mean, considered as transmitters, antennas, like transmit antennas. So they would be, uh, equivalent to this to RF antennas. Now they are transmitting it information for uh, towards the receiver. Now, in case of a RF system, having a MIMO systems becomes is complicated. You need a lot of RF chains, so there's a lot of compute involved there for each RF chain. And as we move to a large MIMO and now massive MIMO, looking at 5G and all, we are now saying that okay, because all of these RF chains they require a lot of energy and not feasible, practically also not possible to implement for many of our system engineers. So they are not looking at ways where we can use let's say less number of RF chains and still get similar throughput. Some kind of a switching can be done. Some other clever techniques can be deployed. But in case of visible light, I have this MIMO system already in place. If I look at an LED light, so there's a lot of LED tube light. There's a lot of LEDs there. In a bulb as well, if you open it up, you'll see at least 8 or more of these LEDs. And if I say each of these LED is an antenna, I already have a MIMO structure uh, there. So it is inherently there already. So I don't have to do anything special there. Whereas in case of RF, it becomes very difficult. You need to have these antennas and the full RF chain, IF conversion, and also they all those things are removed in case of visible light. Now, in addition to FMS impairments, the performance of a massive MIMO VLC is also limited by ill conditioning of this channel. So that is one problem because these are a massive MIMO channel, but they need to be separated enough so that they are independent. But in practice, they are not. So there is a special correlation between the channels because they are close to each other. So they and again, because of nonlinearity also, they uh, would not be having a complete independent path. So there'll be some leakages between them. So there is a correlation between different of these, and they increase as the number of antennas increase or number of LEDs increases. Now this inversion of this L channel uh, matrix. So the easiest way to, let's say, do an equalization, or the first thing that people try to do is do an inversion of the channel. So if I'm doing this inversion of this ill-conditioned choice, that results in noise amplification, which then degrades the overall BR performance of a visible light system. Now, to mitigate these issues, there are various solutions. So one way is to look at pre-distorters at the transmitter end, and other one is to look at the post-distorters at the receiver. So post-distorter also you might have heard with the name of equalizers, and pre-distorters would be at the transmitter end. Now the throughput of existing VLC systems can be increased if you are able to fix these problems. So let's look at this. So the simplest solution that comes to mind is in reference number 6. Okay, it's a very old but very simple and easy solution. Uh, is where, let us say that the LED manufacturers were to publish the they'll publishing their LED characteristics, and from that, if I can draw a lookup table, we make a lookup table for different values of input. I get what output I get. Then at the receiver, I can do inversion of it. I can do a pre-coding as well, the pre-distorter. So here, this the solution is a pre-distorter, where after the LED, I can do this, or I can do a pre-distortion before passing the signal to the lookup table, so that ultimately the convolution result of this artificially added pre-distorter and the LED nonlinearity gives me a flat response. Now there is a limitation that's not suitable for dynamic uh, modeling of dynamic these nonlinearities, because things change, because the LEDs over the period they will change their characteristics, also the temperature and humidity things will change, um, and also there is mobility, and let's say you designed a system with a particular LED, but after 5 years, 10 years, you need to change it, then you might have to get another lookup table. So it is not really very practical way of solving this problem. Um, Hence, people move towards adaptive solutions. So, adaptive linear, non normalized least mean square based learning was proposed by Kim in reference number 7. So, they deliver
I think there may be some network issue from the side of a professor, so he will join in few minutes.
hello, can you hear me now?
Yes, sir. Yes, sir.
Yeah, sorry, there was a bad connection.
Network issue. Yeah, yeah.
Yeah. So we are back here. So Kim has given a solution on using adaptive linear normalized least mean square algorithm. So uh, let's say if you are familiar with optimization or adaptive signal processing, so least mean square is one of the very popular algorithm that has been used in various applications. It is a very old, I'll say 40, 50 years old or even more known algorithm that has been applied to various solving problems, still very valid. But this solution, given in reference 7, delivers suboptimal performance as LED characteristics are non-linear. So the premise here is if I'm trying to solve, let's say, a nonlinear predistortion problem or even equalization problem later, I need to use or my structure of the system to be nonlinear in nature. Solving linear problems with nonlinear problems with linear will not give you good results, although easy to implement, but yeah, they'll not give you good results. So here we propose a solution on adaptive nonlinear Chebyshev based structure. So Chebyshev based structure was nonlinear structure. We updated the weights using the NLMS algorithm. So this relies. So the limitation is it works very well, but it relies on the perfect feedback requirements. So this was one of the very early and very interesting work that we did in published in photonic letters, technology letters. One of the very good piece of work, not very well, but the plots and the values that the gains that we were getting was tremendous, and then we continued on those on that journey for other systems as well. Then so this relies what the problem was is relies on perfect feedback to of detected symbols to the transmitter, because so this is something which in practice will not have. So that is okay. So however, the pre-distorters they rely on the perfect feedback. So this was a problem there. So the work then started to move towards a post-distorter. So in the post-distorters, which are equalizers, right? So one of the again a very active group is of Stefanik. They proposed a DFE Volterra based system. So DFE decision feedback equalizer. They also have been known for many years, and Volterra also. Volterra is one of the very first structures that are equalizer structures are used when we are trying to do equalization in a nonlinear environment. Also very popular in optical networks as well. But they work on the they are categorized in the polynomial series one, and they have a high computational complexity and also modeling errors, because in theory, yes, we can have infinite number of these polynomials, but in practice, usually second, third order, we don't go beyond that. Uh, so in order to circumvent that limitation, we propose a few algorithms based on kernel LMS, kernel MSCI criteria, where we did learning in RKHS domain. So RKHS is reproducible kernel Hilbert spaces. So this delivered suboptimal performance over high ISI, but if there's low ISI, then performed very well. Then there's another very active group, like Gazim-Loy, which worked on ANN and DNN type of equalizer. They fall in the category of neural networks. But then doing a non-convex optimization is a problem, and choice of hyperparameter is another issue. So somebody, I think, typed something. Yeah, so yeah, the citations will come. Yeah, yeah, we'll show them in the end. Yeah. Okay. So here, so you're from Gazem. Um, so yeah, if I look even globally on the visible light, so we have Professor Haas group, Gazem Loy, our group, um, stuff like yeah, a little bit these days, but so this is what three, four people
Uh,
in groups in the world
Sorry, sir. Sorry.
working on
Any
this.
question from the side of Rupinder Kaur?
Oh, somebody raised hands. Yeah.
Sir, actually, he or she just unmute himself. Okay, okay, fine, sir. Please.
Okay. Okay. Okay.
No question.
Okay. Okay, so here there's another issue with using ANN or TNN type of things, that doing mathematical and also giving guarantees becomes difficult, and they're also sensitive to the choice of hyperparameters. That's something we have recently tackled uh, with this, but again the analysis part still remains an open issue in most literature. So our reason for moving towards RKHS or taking that stream was that RKHS based post-dorsal found to outperform this because they do not rely on the polynomial series expansion. They are convex in nature. They have a universal approximation, and they have low computational complexity because we do some kind of sparsification. Uh, there are different criteria. We used one which has worked very well for us, which lowers the computational complexity. So, but however, the conventional feed-forward RKHS-based pose distorters do deliver suboptimal performance over a multipath VLC channel impaired by high ASI and non-Gaussian distortion. And in order to handle this non-Gaussian distortion processes and coordinate visibility, so the VLC, the performance is lower. Um, and also because of user mobility, we need to do tracking. So our work has graduated, I'll say, to a DFE based pose distorters, which are more um, stronger than the feed forward RKHs, because there's a decent feedback equalizer. If you don't know, I'll just give a small that it is like you have an FIR filter, which is like a feed forward equalizer, right? And then you have this feedback path, which also has some this FIR kind of structure, which gives you a certain delay and scaling, and that is then so whatever estimate we do, we try to subtract it from the incoming symbol. So in a way, there is some feedback which is coming from the detected symbol. So the idea is because of intersymbol interference, the interference part of the detected symbol, which is already passed through this equalizer, we could possibly subtract it from the next incoming symbol. Right, so it becomes a stronger, a better way to handle ISI, and gives better performances as well. So that's what we have applied. So initially, when we started working on this area, we looked at the Chebyshev type of some nonlinear structures. Then we moved on to look at RKHS based solution. Then now we're looking at this DFE type of structures. Then there's another interesting criteria is if you look at literature, most of the literature um, will find that we use for equalizers also we use a criteria called as MSE, the minimum mean squared error criteria. Uh, Whereas there are different criteria which are non-MSE one, which are probably stronger criteria, and the one that we have mostly worked on is MSCR. Also, there's one work we did on minimum Varsovia criteria one, maximum Varsovia criteria, but mostly our work has been on minimum symbol error rate criteria, because for an equalizer or for a communication system, an equalizer in the communication system, the end goal or objective of an equalizer is to minimize the symbol error rate, not the MSE. Whereas if I'm looking at an estimator, like a channel estimator, then yes, I need to minimize the mean square error between the, let's say, the actual channel and then the estimated one. But whereas for an equalizer, again, most of literature still considers MSE. Uh, that is not a stronger criteria, I'll say. So we have MSCR criteria, which is much stronger and provides much better uh, uh, rates. Uh, then further, our recent work has been looking at RFF, the random Fourier features one, which is explicit for RKHS based methods, which has become more, actually it seems more better than what we have done before. So there's been improvement in since what we have been working in the last 4 or 5 years. We applied RFF in the recent works, and that also works in a finite memory uh, budget. So let's look at the first problem definition that we have, and if you're less interested, you can look into this reference below to go in detail. So here, our problem is LED nonlinearity, ill-conditioned massive MIMO channel, and DC bias fluctuation. So proposed solution is a hybrid adaptive precoder and a post distorter for massive MIMO VLC channel. So, but in we have a process where we have a LED which is nonlinearity. Um, there's a condition number is also poor. We need to improve it, and then this leads to a, and we also try to improve the performance by using MSCR type of criteria. Now, if you look at this block diagram for the basic system model, we have a Capcom type of constellation. We have a precoder. We have a DC bias array to the precoder. Then there's a LED array. This goes to a massive MIMO channel. We then AWGN is something, So the top one is for the transmitter, bottom one is for the receiver. Then we AWGN, which is a relative wide Gaussian noise. Then a photodiode array. We do something similar to the SVD. We do a inversion, also do inverse here. Then we apply to the KMSCR, which is a kernel minimum symbol error rate criteria based pose distorter, and we update these uh, values of lambda, and we get an estimate of xk. So because it's a training based system initially, so it's a learning system, so we can feed this x hat k, which is estimated at the receiver, to the transmitter. There is a link between these two xk. So there is, it's already known what is xk in the first initial few symbols. So now let xk be the Capcom transmitted symbol. Input signal is multiplied by precoder matrix P at the transmitter. The received signal yk by the photodetector and the kth instant is given by this equation. So ultimately at the receiver, I get yk as a vector, which is gone through h, which is a massive MIMO VLC channel with NR and NT nodes. Then we have the thermal noise and the ambient noise, and because thermal noise we assume to be AWGN, IIT. Also, uh, ambient noise, we can approximate it to be a Gaussian distributed for large degrees of freedom. And where B is a DC bias that I was telling you, because we have to put these. So our input symbol xk, there's a pre-distorter applied P, which is capital P matrix, Peters matrix, applied to xk. After that, it goes through, there's a DC bias added, and this whole thing then goes through the F. So F is the LED nonlinearity. Then it is put onto the channel, which is H, massive MIMO VLC channel. Then we have a noise plus the ambient, thermal and the ambient noise, which is added. And so you get YK as the receiver symbol. Now, how do we model this nonlinearity? So, in the literature, RAP nonlinearity model is one which is very commonly used. This is the equation for the RAP nonlinearity. We have Fk, where x tilde k is the input parameter. Here we have xk minus vth. So this is vth is configurable. So you can look at the literature to find out the values, typical values of vth and vmax that is put there, and q controls the level of nonlinearity. So the symbol is, let's say, lower than the V threshold, then there is no nonlinearity. That means it is working in the linear region. And if it is higher, then it is working in the nonlinear region. Now the channel impulse response between ith LED and jth and jth LED and ith PD is expressed with this equation. That's the channel impulse response, again given in the literature already. And the good part is some of these channel models are now appearing as part of the IEEE standards. So our collaborators, Professor Murat Visal in Oziken University in Istanbul, they have got full setup, and they're very active in this area. So new channels keep on coming from them, and they are standardized. So they are put onto the IEEE standardization committees, and it goes through that thing. So that can be, that's now open, so that anyone can use it. So the contribution from this work is on a novel hybrid SVD based pre-distorter and post-distorter are proposed for ill-conditioned this massive MIMO. Further index used in the pre-coded design is optimized. And lastly, the approximation expression for B are also done, because we want to do some kind of analysis to see, yes, if our algorithm is working fine or not. So how do we do it with the theoretical analysis and find out if the algorithm is going to work or going to achieve this bit error rates. Now, because this is RKHS based algorithm, so we have also from the practical point of view, so in theory, what we should do is with a machine learning algorithm, we should be able to store uh, all the possibilities that the symbol goes through. But in practice, not possible to have a memory of this large size. So we have to limit that memory. So we do some kind of sparsification, and then do put some checks. So using this if statement, we put some checks to see if that realization of the symbol needs to be stored or not, which will be helpful later in the equalization. Because in theory, yes, we should be able to, if we can, save all of them, then we should get very good performance. But in practice, because we have limited budget for the memory, so we can say only say 100 symbols or 200 symbols or something. So we can see that, okay, if I have this fixed memory budget, what kind of performances I'll achieve, because of course I'm going to lose some performance, but how much in theory I can achieve, and that's what through our algorithms, and we try to achieve those values. Now we propose a rhetoric recorder using index-based SVD approach, using TX condition number to reducing the condition number of the overall channel. So massive MIMO VLC channel H can be the decompositioning SVD. So here, if you have come across SVD, or you can, if you're even new, you can play with it using even on MATLAB as well. You can create a channel matrix H where all the elements are, let's say, Gaussian distributed, even not even use the one that we said generally, and then you can use a SVD function to get these three matrices. You get these eigenvalues, eigenvectors. So you have this U in V are the left and the right singular vectors, and lambda is the diagonal matrix with the eigenvalues. The precoder matrix is designed as P is equal to V times lambda, but then this factor lambda k is something we try to optimize, where lambda k is between 0 and 1 is a precoding index. That is something we need to optimize for our problem. Now, first is after subtracting a DC bias and applying Bousquet theorem, we can write this equation number 6. Equation number 6 in this form below. So we can move all of them at one side, and we can call them as our Euler adaptive distortion, and then we can look at how this because the DC bias is not Gaussian as such. It is um, going to be between, it's a uniformly distributed with minus epsilon, a small value. So there's a small variation, but it is uniform distribution. So lambda is uncorrelated distortion with zero mean and covariance matrices, and alpha is given by the expectation of f times x, and then normalized over. So it's a scaling coefficient. The key takeaway is that delta B is a uniformly distributed, but we can still consider this to be overall adaptive distortion, and this needs to be handled. So this can be a non-Gaussian in structure. So first two, okay, we have considered to be Gaussian, but the later two we cannot, because this delta V is uniformly distributed, and this also can be considered as non-Gaussian. So in certain conditions, this can be okay approximated later as a Gaussian overall, but in practice it is non-Gaussian. So here criteria other than MMSE becomes a stronger um, criteria to adapt your algorithm or learn your algorithms on. The proposed adaptive pre-disorder here, basically, yeah, we have to look at this condition number. So performance of precoder is sensitive to the choice of lambda k. So lambda k is something we need to adapt. Smaller values lambda k reduces the condition number of active channel matrix, and the cost of the downside is the cost of increasing a PAPR of the transmitted signal and vice versa. Hence, lambda k should be learned adaptively from the received observation to achieve a trade-off between the condition number and the p, because they are two opposite things. We need to handle both of them to get the gain from the MIMO, or we handle the PAPR. So a good value of lambda k would be is something that we look forward to. So lambda k is optimized using MSCI criteria, index number, by following optimization problem as given here. So this optimization problem is given by, we have this observation or the weights of the RKHS system. So this omega k minus omega k minus 1 um, squared over RKHS base, where we have to minimize lambda k and this weights such that gk lambda k is equal to 0 and lambda k is between 0 and 1. Now gk is for, so this is something that we need to know, and that as a communication engineer will know what type of modulation scheme we are using. So this, for a QAM, gk has this structure. It's already given in the literature. So this is a tan hyperbolic beta lambda r lambda uh, delta r lambda k plus 1 plus tan hyperbolic beta of this for minus 1 plus 1. So we have these two for real and imaginary parts. For other modulation scheme, this will change. So beta is a high enough approximation to signal function. But saying that in communication systems, when the handshaking occurs before the actual data gets transmitted, there it is already decided which kind of modulation techniques is being used in a training based system. So here we say, yeah, the MSI criteria is stronger because it incorporates the higher order statistical error. But whereas case of MSE, we're only looking at the squared error. Now, if I do a Lagrangian for quadratic various function of our equalizer for a precoder, so L MIMO for lambda k is expanded at this equation. So from here, basically, I'm going to put this gk up here along in the equation 6. So so that becomes so Lagrangian is formed. Now the update equation for lambda k with step size is similar to the, it's a, like a, it's a stochastic subgradient type of method. So we have lambda k plus 1 is lambda k minus mu k is a step size, and the first order derivative of this. Now the gradient will be written as del L MIMO lambda k divided by and first order derivative. So the simplification of this. Well, we can move further from here, and maybe we can move on to the results. So the idea is, I think, is clear, right? We are using an a kernel MSCI criteria, so minimum similarity criteria. We are using a massive MIMO system, and we are doing a learning. So this is the algorithm. We initialize k is equal to 1. We maximize the iteration. So we, because again in practice we cannot go for infinite number of iterations. We need to limit them. So max iter, neta and mu k, and then these are different parameters that we set, and then d is the dictionary size, the initial dictionary, and then the other values for dictionary we add in. So here in this while loop is what we do the equalization. So we have xk MSCR is minus of this. This is so d is the dictionary here, k is a kernel. So we map it to a kernel space. In the RKHS space, we consider them to be a linear operations. So we adapt lambda k as per equation number 11 here. Then calculate the error ek as xk minus x hat KMSCR. Because again, it's a supervised learning, and QK is equal to 10 hyperbole, that is also given for this problem. And if max of, so we do an inner product of phi, which is the kernel phi for yk, comma phi of the entry in the dictionary. If this in the in the RHS space is greater than exponential of minus tau 1. So tau 1 is some hyperparameter that you have chosen. Then and qk is greater than lambda 1. Then we can add this entry into dictionary, else will not add to dictionary, and continue and adapt lastly the sigma k here, which is required for the KMS here criteria. Now, we did theoretical analysis as well to determine the expression for BR. The first, the PDF of the overall distortion is found, and then with some approximation. So the first part we can consider to be a Gaussian, um, and this we know is uniformly distributed. So we can combine them together. So this PDF, overall PDF is given by this equation here, because we said it's uniform one, and so uniform over Gaussian. But uniform also we said it's only two values, plus or minus epsilon. So we can characterize this approximately as this overall PDF. And then we can apply these four different modulation schemes. So we applied for MCOM, get this generalized equation. So I'll not go in detail, but basically let's go to the simulation. So how do we validate that our system is working uh, fine, it's doing equalization as expected. So here we use um, practical, again, a type of system. So it's given in reference number 15. Again, you can refer to that. Um, where we have distance between two LEDs, which is 5.8 centimeters, and distance between two photodiodes at the receiver is again 5.8 centimeters. The effective aperture area of detection is 1 centimeter square, then FOV is 10 degrees. Um, Transmitter semi-angle at half power is 10 degrees. Now distance between transmitter and receiver plane is 2 meters. Center of LED arrays is 10, 11.6, 11.6.5 meters. So these are some of the geometries of the channel that we have chosen, and these are given in reference number 15. You can look at them, and these are actually, I think it is one from the standard, or it's from the paper which has been gone into the standard implementation. So if you are, let's say, coming up with an algorithm, suggestion would be, if you, let's say, use a channel model which is given in the standard, then it is more practical, and others can also validate against that channel. Now, 16 Capcom modulation scheme is used with ensemble of 1000 independent runs to get good averaging, smoother curves. So wrap LED nonlinearity parameters zero point 0.5, and we mix again given in one of the references that we have chosen from the I think it is from it should be from the uh, manufacturer's data sheet. And in 11, lambda k is initialized as 1. For k is equal to 1, beta zero point 0.5, beta is zero point 0.5, lambda is 0.005. So some initialization of these hyperparameters we need to do. Then initial kernel width is set as per Silverman's law. This is if you are uh, done any work on non-parametric estimation, PDF estimation. Then Silverman's book is very nice. It's a very small, thin book, but very good. They've given a rule how you can choose variants of different kernels, width, what width you can choose. So we'll initially start with this kernel width. That's a good starting point. Actually, in some literature, it is the end point as well, where you don't adapt this kernel width. The step size of 0.35 and mu h of this is chosen for these algorithms. And what we find is that the proposed algorithm, they work uh, very well. If we were to use a linear LED structure, if we assume there's a linear one, then no pre-coding is used. Then the green one are the rates that we uh, that we expect. But for um, the case where there is a DC bias error, there also we see that our algorithm works better, and it is changing because we are saying that this bias will keep on changing. If there's no DC bias, then yeah, this is overlapping with uh, the best possible in theory. But in case of a if there's a DC bias, then slowly the graph starts to go up, the performance starts to decrease. So if you look at, let's say, this magenta, this triangle, for DC bias error of 0.06, then the curve has gone upright. So it is so at about even at 105 dB SNR, we are getting 10 to power minus 2, where and it has tapered as well. It is it's not getting any improvement. It's not like a waterfall model. But if we do not have this LED, this bias error, then in that case we expect this um, a smooth waterfall kind of drop. Now, this is what we are seeing here, that for achieving the performance that we see on the left hand side, on the right hand side is the size of dictionary that we need. The dictionary size of these many symbols we need to store. Um, and on the x-axis shows how many iterations. So after about uh, 200 300 iterations, we are seeing a stabilization. There's not much entry or things are added into the dictionary, and the size is now stabilized. So even if something is added, it is actually the previous entry is replaced, and then the new one is added. This is for a 16 cross 16, sorry, massive MIMO system. So in visible light case, 16 cross 16, we can in literature we can classify this as massive MIMO, whereas in RF, yeah, we generally go 100 plus to classify that as massive MIMO. So here in 36 cross 36 massive MIMO, so we see similar sort of trend. So the major observation, the proposed algorithms delivers about 10 to 14 dB gain over uncoded scenarios. The proposed algorithms converges to lower dictionary size as compared to proposed and the one the conventional one. The analytical BR also we have found, and that it overlaps for different values of epsilon, which rectifies the present analysis. Now we can look into other works by taking so, um, do a BR analysis in detail. So I think in interest of time, I'll probably try to skip this one, and we can just look at this structure for DFE structure that I was telling. So it is, um, you can say similar to the back propagation that we do in machine learning, where you are getting some feedback from the output back to the input to improve the detection performance. So here, if you look at this is a DFE structure. Um, so the transmitter is on the top, and the receiver is at the software AWGN photodiode. Now this red, highlight one. This is the DFE structure. So we have a mapping from RKHS and feed forward filter, and also feedback filter. It gets uh, added here. DFE structure. And I was telling about this standardized channel. So these are the standards. So IEEE 82215 PAN VLC channel. So you can go online, search for it, and use this channel model for your research and further exploration. Again, similar model at the input, but here our focus is on the equalizer, right? The post distorter. So we're not doing anything on the pre-distorter here. So we will. So yeah. So the pre and the so we have a feed forward and feedback path, which is this one is a traditional DFE equalizer structure, but here our learning is in the RKHS domain. So propose a joint optimization problem. Wait, update. This is the algorithm. We'll skip this one. Now results wise, we tried four different scenarios, and this they are given in the literature. You can look at and that in the IEEE 82215.4. Now this for the open office scenario where we see that the proposed algorithm works better than Volterra DFE one also works good. And then the KLMS NC criteria is one of the previous one that you proposed works good as well. But the best one is the proposed with the DFE structure. The DFE structure are stronger for nonlinear nonlinearities, handling nonlinearities, and they work better in while using lower dictionary size. So that is an important aspect that you can get good, better rate performance, but with a lower dictionary size. Similar thing we see in office with cubicles scenario, then open office. Yeah, I think yeah. So I think we can open. Should we open for question and answers now?
Yes, sir. Yes, sir.
Yeah. Okay. Okay. So yeah, please. Yeah. If there's any questions, then please. Yeah. Feel free to ask.
Any question from the side of participants?
So you can unmute or maybe type in the chat box.
Yes, yes. I think, sir, one student is asking for the citation number 12 and 13.
Yeah. Yeah. So this should be at the very end. Okay.
Any other
Let me
question from the
search
side
for
of
this one.
participants? So I think, sir, there is no question.
See my screen. You see my screen there. The one by Gazemloy.
Sir, yes, yeah, right now it is presenting. I
Present.
can
Yeah.
see.
Okay. Yeah. Yeah. So this is the one in general lightweight technologies. Lightweight technologies. So this is one you can look at. This is using artificial neural networks, based equalizer, published in 2014.
Any other question from the side of participants? If no question, then we are going to end this session.
Okay. So if anything, yeah, even later as well, if anybody is interested to carry this forward, or look at some research collaboration something, so feel free to drop a short email. Um, and yeah, this is a good book as well to refer. So by Gazem Loy.
Sir,
It's right on
Abhiranjan is
very end.
saying just 12 and 13 citation number.
Yeah, so this one is the one actually. This is the one because they were using it was for the neural network part. It is this one. The where was it? It was yeah, this one. It was using neural networks based equalizer. So they have Gazimloy. They have done a lot of work in this area as well. So and popular as well. So you can yeah look at this reference number 13. But this one is a book. So book generally you will have higher uh, information. Uh, so you can refer to his book as well on visible light. I think where was it? It was here. Yeah, yeah, yeah. There's a later reference, but yeah, this also you can refer to.
Any other question? Okay, fine. So, thank you, sir, sharing your wide research experience in the field of visible light communication, and I'm sure this will be helpful for those who are working in this field for finding the new problem statements, and those who are willing to work in this particular field. They will get the basic ideas what is exactly problem in the visible light communication. So this will help them to find the problem a beginning problem early stage of the problem statement and the carry on their research work. So sir, thank you so much for giving us time.
Okay, thank you very much. Yeah, thank you for inviting me over. Yeah, so the reader can you look at these two references. These are based on the neural network and the DNN type of architecture. So these are the reference, the Gazim-Loy one and the other one, the next one below. So you can take a screenshot if you, want to go in detail. So these are the two papers that I was referring to. So thank you very much, and all the best for the rest of the sessions that you're going to be
Thank you, sir. Thank you so much.
holding. Man. Thank you very much indeed. Thank you. Thank you. Bye bye.
So, all the participants, this is the end of this session, and the next session will be resumed at 1:55. Thank you all of you.